by sets, that's a pretty open topic because, as I have here on the board, sets are defined to be a well-defined collection of objects called elements, which leaves it pretty wide open. Normally, of course, we're talking about sets of numbers. Say I'm talking about the set 1 through 5. 1, 2, 3, 4, 5. The counting numbers 1 to 5. And so this is our set here. This is the way we'd write that set, or one way we'd write that set, just by listing out the elements. Each of these in sets is called an element. And then the little squiggly lines around that, those are referred to as the set braces, and that's how sets are designated in set theory. But as I was saying, sets are pretty wide open. They can be sets of numbers, they can be sets of letters. We could do a set of students, write out that, a set of shapes. Really, it's pretty wide open what sets can be made up of. Now, this little term here, well-defined, what we'll try to do is always be well-defined. And by well-defined, we, of course, what I mean by that is it's a set that is something that can be reproduced by anyone. For example, if I said the set of counting numbers between 7 and 11. Well, as long as you know what a counting number is, you can reproduce that set, and your set would be the same as my set. That would be 8, 9, and 10, counting numbers between 7 and 11. That's what we mean by well-defined. Where you run into some difficulty is, with things like these would not be well-defined, the set of good numbers. Your good numbers would be different than my good numbers and somebody else's good numbers. So that's what we mean by well-defined. It's a set, a collection that can be reproduced by anyone. All right, a couple other notational items. For names of sets, like if I wanted to name this set A, such as give it a name of A, usually capital letters are reserved for the names of sets. So capital A is our set 1 through 5. Now, let's say I do set B here, and B is going to be letters, X, Y, Z, and notice there I use lowercase letters. Just a general rule of thumb, it doesn't have to be such, but as a general rule of thumb, uppercase letters for the names, and then lowercase letters for our actual elements there. Okay? All right, and also, this is, we were talking about this one earlier. Another thing to point out here, this is a couple ways, different ways we can do sets. Of course, here we've got our listing method, and a lot of times that's the way we'll do it. But here is the word description for our set. So different ways we can talk about sets and what we mean. There is one other method of describing sets, and it's kind of a combination of these two things, the listing or the braces, and it's called the set builder notation, and I mention it here just to for your information. set builder notation. Let me just give you an example here. Write it out here and I'll tell you what it all means. X is a counting number greater than 10. Okay, yeah, this is set builder notation. We got the set braces, but then we kind of have some, we got a description, but then we've kind of got some other funny notational things here. The way this is read, it's read the set of X, so that's kind of gets us started here, the set of X, and then this vertical bar here, in this case, you can read that as such that, and then X is a counting number greater than 10. Okay, so it's just a little bit of notation. Sometimes you'll see it. Sometimes this book will use it. But just so you know what it all means. Okay, now, another point, let's kind of play off of that. So we're talking about which set? The set of counting numbers greater than 10. Well, that would be starting at 11, 12, and 13, and then everything thereafter. So we wind up with this infinite set. So let me make a quick point about infinite and then another term here. Yeah, there's some sets will be infinite, and matter of fact, some sets can be infinite in a lot of different ways. This one just keeps going to the right there, so but that's obviously infinite. Now, the other sets I have up here, for example, this one, not so much infinite here, and so there's another term there associated with those that have a start and a stopping point. Those are called finite sets. So a finite set is a set that has a starting point and an ending point. Infinite sets may have a starting point and don't have an ending point, or may not have either one. They may go out infinitely both ways, but a finite set has both a start and a stopping point. Okay. So yeah, if it asks about finite or infinite, that's finite just is kind of the opposite there of infinite, where you do have a starting and a stopping place. Okay? All right. One other quick mention of a notational thing with sets. Back to the elements here. Let's say A is 1, 2, 3, and 4. This symbol here is, you see that a lot in set theory, and what that means, it means, or is read, is an element of. That's what that symbol means here. So 1 is an element of A. 2 is an element of A. 3 is an element of A. So we could write all those out. But yeah, if you see that little symbol right there, it just means is an element of. Now, if we get a number, such as 5 here in this case, 5 does not